Test. All right. Okay. DFM feedback. Yeah, got some feedback. We have to go through and implement it, and some of it's pretty painful. So the good news is the DFM for these columns is pretty simple. It's just the radius on the end mill, and I have to change these, which is not the end of the world. But the DFM feedback on this guy was painful. So the concept here was that the pendulum would have a threaded a threaded detail on the end here, and that would go into the nut. They can't thread this for M12 175, which is a problem because it isn't just like I can replace this with a bolt. The issue, the challenge, is that this cable for the encoder on the second pendulum has to pass through the pendulum down here. And I looked at McMaster and they don't sell hollow bolts. So we have to figure something out. I did find threaded studs, which were hollow. But I'd have to cut this down to size potentially. So I'm not in love with that as a solution. I'm not in love with that. It's also expensive. I think there are also hollow standoffs as a potential solve. Something like this. But I don't think they had a size that made sense. So essentially, I need this to be, let's see down here, about an inch long. So I would need an M12. It doesn't have to be M12, so actually we shouldn't specify that, but we should say roughly 25 millimeters. And it gets even more complicated. So I can't just use a standoff here like this because it has to sit the inner ring of the bearing here. So that's a problem. And it also has to have a step detail here, which I might be able to figure out in designing into the existing sort of pendulum design. But anyways, long story short, I need to get that figured out. And I don't know what the solution is yet. So we're going to work through that. Yeah, so let's do that. The first thing I'll do is take a quick look at, well, actually, I know I can implement the DFM feedback for the columns. So I'm going to do that really quickly. Then we'll get back to the problem I just described. So the problem was, I think this was a millimeter radius. Yeah, needed to be at least 3. And then this one had to be at least 3, I believe. I don't know that I have a very fast way to change this to 3. Maybe negative offset. Oh, broke it. That should be 3, yeah. And then I guess I could just move this back in line here. Not sure that's actually gonna work. Maybe it will. Yeah, it does. Perfect. All right. Easy enough. Oh, actually, I have to do that to the other side as well. So, okay. All right. So I'll just split this part into 2, and then bring that detail back over here. Done. Okay. So that's the DFM feedback for the column. I'm going to do that again here for the taller one. And then, yeah, just remove this radius. We said 3 minimum, but if I just get rid of the radius, then I think we're fine. Okay. Looks like it worked. Yeah. Edge distance here might be a problem. I don't think it will be. Let's see. I don't think so. We'll see what they say. If it is an issue, we'll just slot that. Actually, maybe we should slot that preemptively. Yeah, we should slot that preemptively. I think they're going to come back and say something about that. So we'll do that real quick. Essentially what I'm saying is that the edge distance between here and the top isn't going to be probably what they want it to be. So I'm guessing maybe a millimeter and a half or something like that. So we'll just slot this out here where it doesn't matter. It only matters down here. Let's see how we would do that. Let's pull that hole and this geometry, and then we will, I guess we'll create a Boolean to do, we'll just create a solid to do a Boolean with. Not sure where I'm going with this yet. Yeah, I'm not sure where I'm going with this yet. Why didn't this close out? Yeah, why didn't this close out? Maybe this, yeah. Should be fine. Still not. Yeah, whatever. I'm not even sure this is worth doing yet. So let's just go back. We'll do that slot just by doing a top view of it. Okay. Let's see. And then that should extrude. I'm going to do body for now. And then try to pick up the lowest tangency on this fillet, which I think is going to be this line. So I'll use a plane for that. See if that works. All right, this should spit out something reasonable. Yes. Okay. Yeah. Okay. Looks a little odd, but it's gonna be. It's gonna break. It's gonna fix any issues that they have with edge distances. So minimum edge distances, that is. Real quick, I should check to see if this is working. And it is. Cool. Okay. let's just propagate this, fix that real quick. So same deal, slice down the middle, mirror it. Yeah. So before we do that, let's pull this geometry over to the other column, because that's going to simplify this. Okay, and then replace face. Continues to be my favorite tool. Let me turn this into a copy. I forgot to make that a copy. Right? What did I do there? Oh, I see. Yep, that worked out fine. Okay. Okay, I think that's right. They might get me on edge distance for this now, but wait for them to say something. And we'll pattern this. There we go. Okay, so that's the column DFM done. Now we have to figure out what we're going to do with this. This spooks me. Okay. Yeah, not sure what to do about this one. So I gave it some thought. Another solution would be to actually buy an aluminum bolt. An aluminum shoulder screw. The problem with that, let me draw it out. So I'll hide this to show you what I'm thinking. So what I could do is redraw the pendulum. So the pendulum would come in and sit roughly here. And it would pick up this ledge as it was before. Yeah. Yep, like so. This would be hollow. Then I could come in with a bolt. With a washer, like so. And then this would potentially thread here. And then we would tighten with this nut. But the problem with that is that I need a hole in the middle of the bolt, right? And so that means it can't be a socket head cap screw. And you know, this I'll figure out later. But I need a hole in the middle. So I was thinking, well, I could just buy this screw and send it to a machine shop to have them hog out the middle. And that means I wouldn't be able to use like a grade 8 bolt because it would be super hard and they would hate having to machine that, but I could do it with an aluminum bolt. It would have to be hex. It wouldn't be able to be a socket head cap screw because then you would then you'd have the issue of actually machining out accidentally the hex head, which you would use to actually tighten the thing. So I can pick up aluminum. There it is. Flange material. It's not right. Just go to screws and pick material. So hex head screw. There you go. Aluminum hex head screw. Was looking for roughly 1/2 inch, and they have 3-inch. So yeah, I mean, this could be a solve. It's just I'd have to find a shop locally to hog this out. Technically, I guess I could do it myself. I could chuck it into my vise right here, right there. Technically, I could do that, but in the effort to keep this open source, I would, well, technically, yeah, and I want to keep it open source, so I don't want someone to have to do their own milling for this. I want them to be able to buy all of these parts. So another thing I was thinking of was, yeah, just use a screw, don't hog it out, and just route the cable here through a spacer or something like that, which might be able to work. So in other words, in this diagram, the cable actually juts around like this. It finds a way to go through this spacer and then out. That might work. We could probably do that. I'd have to see it in all, I guess, in 3D to really grok if it's going to work well. The problem is we have to find space in between the bolt and the inner ring of this bearing to make that work. So why don't we cut out what we know won't work, which is going to be this threaded portion. So now we still are doing everything we need except for the preload. We need to find a way to get the preload through. So we then would use a screw and we can adjust this. And we'd want to use a shoulder bolt because we would like a decent bearing surface between the pendulum, the screw, and the inner ring of the bearing. So let's, roughly speaking, see what that dimension would have to be. This would have to be, so 20, we need it to be at least 25 millimeters long, and then you want some engagement here, we'll call that to here, we'll call that 10. So 35 millimeter long shoulder screw. The reason shoulder screw over regular screw is that I can't control the shank here on a regular screw. So shoulder screws, they will guarantee a fixed shank diameter and length with a tolerance on the shank, which is really nice. So actually, can we get clever with this and say, actually, our inner ring will be bearing on the OD of that shoulder screw. And just hog all of this out. No, we don't want to do that, right? Because we need a passageway for the cable here. So we're not going to do that. Okay, so back to shoulder screws, roughly 35 millimeters. Shoulder length actually is going to be a better way to define this. So shoulder length is going to be like I think I said 25. Yeah, roughly 25. The problem with these is that they have super long lead time. I've bought these for projects super frequently, and I think, okay, everything in the order. I mean, McMaster card will be here in 2 days, but for some reason, I think they actually machine shoulder screws to order. So that's been disappointing. So the lead time is like 2 weeks in a lot of cases. Why is that linking to this? I think their site's broken. That's funny. Okay. Anyways, back to this. So we want steel. It's cheap. Roughly, what's the diameter on this? 7? Could be 8. So an M8 sounds about right. So let's look for an M8. Shoulder diameter, 8 millimeters. Roughly 25. Don't know how I feel about the M6 termination. Let's see. Delivers tomorrow. Okay, so they won't have to machine this down. So 25 and then 11. That's roughly 35. That's roughly what we wanted. This detail is going to change pretty drastically, though. Man, not loving the way that this is going. Not loving it. Okay, pull this in. Is this right detail? No, that's not right. That's right. Okay. All right. That's what we want. So ignore the cable. It's going to look wrong for a while. We're going to reroute that somewhere. So technically this would slap in and we would just have to adjust this nut. Yeah, we'd have to adjust this nut. I don't know how we do that, but I mean, I do know how. I'm worried about how do we deal with this. This part becomes really complicated. Unless maybe we can find a super wide nut. So this is an M6 wide nut. Or a nut with a wide washer, maybe. We want it to be thin. Actually, we don't care about that. We just want it to be big. 10% is not enough. I think we need a wide washer. That's really what we need. Let's see. M64, that's not. What the heck? All right, let's try this again. So we have lock, yada, 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 weld. Actually, weld, that would be nice. No, that would be nice. Yeah, their diameter isn't big enough. just for giggles. Let's see. So 19 diameter, and we need essentially from here to here. Well, that. I mean, technically that might work. Let's see. If we bring this down to 19, what happens? I mean, technically that would work. Yeah, technically that would work. I don't know how I feel about it though. We don't have enough space in here actually for getting that cable through, so that wouldn't work. So I think we just get a standard nut. Standard M6 nut. $1 millimeter. $3. It's cheap, affordable, not cheap. We're gonna see what this looks like. This is really half of engineering. It's just being told you can't do something and then finding another way to do it. Truly. Okay. So just for giggles, what would be a big washer that we could get on that? Let's find out. We could keep this just being standard parts instead of something we have to buy. That'd be nice. Although we do actually we might have an opportunity. No, because we need this thread here. And now we have to worry about how do we attach this thing. Yeah, okay, so this actually, that's dumb. What we're gonna do is we're just gonna make this an M6. What is an M6 tab size? I'm gonna bookmark this because I keep saying I will. M6 by 1, that's a 5 millimeter tab. Okay, that works again, roughly speaking. It almost works. We have to figure out what we're gonna do with this cable. And I just guessed 3 millimeters. I don't actually know what it's gonna be. We have to pass signal for 1 encoder. So that bundle, we can actually take that down to, I think, no, I do think it actually has to be 5 wires. Let's see, just this encoder, yeah. So I think my caliper's out of batteries, funnily enough. Barely got juice. So I think this is gonna be, I don't know. Yeah. 7 millimeters. All right. I was really cutting it close there. Off topic, actually. Check this out. Just got my first cast part from Digital Metals. Check that out. Ordered on Sunday. Had it to me by essentially today. Crazy. It's this part right here. It's pretty cool. Yeah, I essentially posted, complained. I didn't complain. I just said, God have mercy on whoever has to program this. And then they just, someone was like, hey, why don't you cast it? So I did. Pretty cool. They even threaded it. Connor's a good dude. Okay, so how do we fix this? So we're going to tap this biggin. From 6 now, so we fixed that, but we have to do something with this cable. Is that enough? I can add washers here if I need preload. So what I'm saying is, imagine if this actually came in a little too large, then I would bottom out on the screw, and then I wouldn't be able to develop preload on the bearing ring, and that would be no good. So actually, this should not be 25. Because, I mean, I guess I could add a washer. I'm going to have to add a washer here anyways. Yeah. This is aluminum. This is steel. I should be adding a washer. Be a good little design engineer and use a washer for a change. So, yeah, cable. What do? Let's isolate the slip ring cable, retaining cup, bearing, and pendulum, and see what we got to do here. So what I'm thinking is we literally, I think we might be able to just cut a slot in this thing. I forgot the screw. Okay. I think we might be able to just cut a slot in this thing. So we could cut a slot. Remember, this is the inner ring of the bearing, so this can't change. This can change. Just for, you know, what is that distance? That's 3.5 millimeters. So we're actually going to have to do a no-no and slot this inner ring retaining, inner ring locating feature. So that's a little annoying. It's a little annoying. Why don't we just pull this all the way through since, you know, see what they say. So this is a threaded hole now, and they go down as deeply as they can, and then we have to add a slot through this nut and this feature here. Let's see if that works. Before I do, I'm going to take a snapshot so I don't forget where. Not so I don't forget. So in case this doesn't work, we can just quickly revert back. And so we are at, what are we at? 1. Actually, I'm going to organize these. I didn't realize how good having PDM and Shaper 3D is until I saw someone using SolidWorks or something recently and realized I just take for granted that I just quickly throw files around in the PDM built into Shaper 3D and pay it no thought. It's just there and it's readily available and syncs, and I don't have to think about it. It's actually now one of the most important features about it, and I never really think about it. Okay. So simple slot, and we'll see what happens. This is kind of a problem because this is actually not a good idea. So when you, here, I'll show you the engineering reason why. Learn this in an interview, actually, and I got nailed in the interview for getting this wrong. I then asked the interviewer, hey, well, actually, where do you even find the answer to this? I've looked at my mech solids book backwards and forwards 15 times. There's no way I missed this. And he said, oh yeah, it's not in the book. It's like, okay, cool. Well, at least I know it now. All right, so if you have a tube or a member, a closed section, right, and you apply a torque, the stress in that is TR over J. Super easy, right? R, T, and J is a function of that cross section. Super easy. Now the problem with open sections, say ones you see frequently, like a wide flange, an I-beam to the layman's, like this, is that you don't tie the top and the bottom. You only do it through the web. So that's an open section. And so the second I cut a slot in this, like so, TR over J doesn't actually happen anymore. It's a open section, and this is going to want to pull over and bend into that. And so you get way more torsional deflection, and you get way higher stress. And so you actually want to avoid that if you can. And the reason why it matters in particular for us is because we were about to do it on our nut. And so if we slot this nut, now all of a sudden when we go to torque it down to develop the required preload, it's really going to just open up and be nasty to kind of get in accurately. So we actually don't open this up. Instead, what we want to do is add an access hole somewhere. Leave it as a closed section. So how do we do that? So we could slot this and then add an access hole over here in the nut somehow. So let's start with that and see if that gets us anywhere. We'll give ourselves, we're going down to 5.5 anyway, so we'll call it a 6mm slot. We want it to go essentially all the way to here. So I'm going to project that geometry so I can pick it up for reference. Work. Y. Project this. I project this. What am I doing wrong? Oh, it's because I had it selected. Yeah, okay. So now here's our slot. So now we need to cut this through. Just going to go all the way down as a solid and then find the placement for it. Is that not perpendicular? What happened? Did I pull the wrong view? Okay. Let's see if I can just redefine that plane. It's fine. Okay, let's find the right place for this. So let's actually just pull it to the center of the rotation axis and see what that does. Yeah, not really a fan of this because the bearing surface is going to be, it's not going to be sitting there, which is, I mean, essentially the inner ring of that bearing's not going to be fully supported, which really annoys me. Some radius so we're not cutting the cable. Same deal up here. Why does that look different? It's off center. Can't win. Cannot win. Redo that. So again, seven, pull it out to this feature. How can I quickly do this? I think I can replace face. Hopefully that works. No, it did not work. How do I get that? It's weird. Yeah, more brute forcing. Just going to develop the planes I need. So that is going to go here on this midpoint, if there is one. Honestly, it doesn't really matter, so just to keep this moving, I'm going to see if I can trick this. I think that's working. Okay. And then we'll slice this again at the axis center. Try again. Okay. That looks right. And so I guess we can just kind of, yeah. Add a radius here. Again, we want to baby this this cable. So okay, let's see what happens. That's a thin section. We have to figure that out. So probably offset that. How would I do that? Easy enough. I don't know. We have to give ourselves enough room for this pass through here. So I'm not sure how we're going to do that. Let's go back to this, maybe pull that down to here. I think 8 worked. Yeah. Okay, so now we have a slot to get the cable through. I really do not like this at all. Look at this. I isolate just the bearing and the inner ring so you can see just how much unsupported section there is here. Yeah, I mean, come on. That's very bad. You just make it, no, we'd have to make the bearing bigger. I mean, we can find out if this is, Apologies for the dog. She chirps once in a while. She thinks she's a bird. Is there another way to do this? Like, do we have to pass it through the center here? Actually, I don't think we have to. We could maybe just pass it through the outside. What would that look like? So we would tape it down to essentially everything you see here, and then we would just pass it to the outside. Would that work? Let's see. Okay, so we leave this as is. Then we add a big honking hole here to pass the cable through. And we route it through a hole here. No, that doesn't work. Yeah, because this doesn't move and then this does, so it doesn't work. So we do have to go through the center somehow. It essentially has to get through the center ring. Okay. Is it perfect? No. Will it work? Maybe. So now we have to add a hole here. Okay. So I need a hole in between these two edges. So 5's a little too much. I think we said we need 5. That's going to kill our edge distances there. But I think we can make that work. So how do we do that? I think we have to get closer to this side, which is fine. So let's pull this geometry out. We can use this to set minimum edge distance. So let's say it's 2 or 3. Yeah. So now if we pull this geometry through, what happens? Let's see. It's kind of odd, but it isn't a hollow section. I mean, it isn't an open section, so that's good. I think I'm going to get in trouble for this. I think the threads are too tight there. Maybe we can move it up. Yeah, it's weird, but it's weird, but it might be necessary. All right, we're gonna try this. You know what? Why not? Besides the fact it might not work. Besides that, why not? Am I really, is this actually an open section? No, actually, it's not an open section because we close it out here. So we could actually go back to the slot idea. So let's try that. I actually don't need my hex detail all the way around. So you got 1, 2, 3, 4. Yeah, you've got 2 ways to get a hex around that, so this actually will work. 1's too much. I mean, 3's too much, 1's just right. And that doesn't go through the entire section. And we can actually pull that out a bit to give ourselves that little bit more meat on that closed section. And let's see what that looks like in context. Maybe we don't want more meat. That's really tight. Let's see what that interface looks like. I mean, not a lot of room over tolerance. It's just, yeah, I mean, we'll try this and see if the DFM comes back with any feedback about that. Okay, so now the cable should be able to flow. How does this actually work? No, we still need an access hole over here. We need a cross-drilled hole. Because it's going to be sitting inside of here. Yeah, so we have to pull it out here, essentially. So let's do that. What happens if I, no, we can't put it there. There's going to be minimum material condition issue there. So they probably won't be able to do it. Well, actually, what's the diameter of this hole? 5. But we want the cross drilled hole to be 6 because when they fixture this part again, if they have to for the second op, it might be off slightly. You don't want to be out of room there. And actually, I just got my answer with this actually needs to be whatever this width is. So see, that's 5. So it does have to be 5. Dang, it's fine. It's going to look a little odd when they spit it out, but, you know, whatever. Okay, so we actually have a solution here now. And do we need them to go all the way through both sides? Just want to see what this part looks like. Not a lot of material here. Is there a need for it to be? No, we can actually make this further out. No reason it needs to be this close to that edge. So now we should be able to thread it through. Yeah. Again, not a huge fan of this. I'm not even sure how I get this out. Oh, actually, there's our answer. We can't get it through because of the screw here. So you have to move that back. So I'll undo that. Not really loving where this went. Let's see if we can do a blind hole. They might be able to swing that. Okay, so now this is what the part looks like. Yeah, I mean, yeah, it is what it is. I mean, how do you, yeah, it is what it is. I mean, we'll see if they can do it. It's the only solution that comes to mind right now for this problem. And while this is broken, I'm going to cut this cable so that it stops developing an interference. Actually, maybe I don't need to cut it. Maybe I can just get it roughly right. That's about it. Yeah, that's about it. Okay. And then we can give ourselves more room here. There's no need for that to be so tight. Right? I'm missing something. Yeah. Okay. Definitely one of the sloppier design decisions I've made in a while, but desperate times, etc. Okay, and I have to copy this detail up to the top now. Yeah. So what moves along? This now changes. This is going to change. So I'll just slice that out. Oh, actually, no. This one is simpler because I don't need to pass through here. So I can actually do this the correct way. Yes. This one should be easier. Let me copy over what I think we're going to need. Which is the screw in that nut. This has to open up, obviously, to be clearance hole for that shoulder screw. And that might be that easy. That might be that easy. I hope it is. Yeah, it is. So you can make the argument, well, you want to develop preload on this inner ring with this part fully, and you want to modify this, but honestly, what's going to happen is they're going to have this tooled up with the billet ready to go, and instead of programming it twice, I actually think net across, like from handoff from me to the part getting cut, it's actually going to be easier instead of having them cam it twice to just make this part with a few extra features twice. Really, it's a deep assumption on my part, but I'm sure the team or someone listening will correct me about that assumption if it's wrong. So here's 10 things you're not supposed to do. Do with that what you will with that information. So, okay, I'm going to send this out, and hopefully that's the end of the DFM, and they start making these parts. And I will see you next time.